I guess, hello, welcome to the last CNSA Active Matter seminar series of the year.
Not of the academic year, barely.
Just of this year, not academic, just of this. We'll be back next year, but for the last speaker, we're delighted to have Luca Giomi from Leiden. Today, he'll be talking to us about hydrodynamics and multi-scale order and confluent epithelial. So, please, Phil, take it away.
Yeah. So, hi everybody, and thanks for having me. Thanks for inviting me to this series of seminars. Today I will do something that I typically don't do, namely to discuss about the work in progress. I don't do it usually because I like to convey sort of complete, well-rounded stories, but this time I could not resist because a lot of what I'm going to be saying started exactly at Harvard, namely in 1978, which accidentally is also the year when I was born. Okay, so I'm Italian, you know, I'm superstitious. I could not resist, you know, to follow the occasion. So I spent, 3 wonderful years at Harvard, and I have so many good memories of it. One of these memories is something that my then mentor Mahadevan told me once. So he told me that a great theory is a theory that still works well beyond its regime of validity. Maha was talking about the Foppel-von Karman theory of plates, which describes the large deformation of elastic plates, even though it's just a little bit more sophisticated than the standard linear theory. But what Maha said then certainly applies also to hydrodynamics. So the terminology hydrodynamics literally contains the word water in it, is hydro in Greek. And yet, in the past few decades, but mostly I would say in the last decade, the boundary of hydrodynamics have been pushed nowhere close to understanding how water flows, okay, very far away. For instance, hydrodynamics has been used by Falkovich and co-worker to describe the flow of electrons in certain two-dimensional materials, such as graphene. And in 2019, my good friend Denis Bartolo wrote this wonderful paper for Science where they used active hydrodynamics to describe the propagation of waves in pedestrians, in crowds of pedestrians, such as the runner of the Chicago Marathon, but before they start running. Nevertheless, one of my favorite applications and one of the subjects in hydrodynamics that we are trying to develop here in my group has to do with the hydrodynamics of collective cell behaviors. Okay, so the fact that cells, collections of cells, tissue or cell layers can have a hydrodynamic behavior, can flow like fluids, is now an experiment, is a piece of experimental evidence, I would say. It's a piece that started more or less in 2010, shortly after, when people were able to demonstrate that indeed, in certain situations, cells are able to collectively flow, just like liquids. What you see in this beautiful movie, this is a paper, a really pioneer paper by Shavit Repar and Jay Fredberg. What you see is an apparatus that is called the wound healing assay, and is meant to mimic the response of a tissues of a system of cells to a scratch. Okay, so cells can be solid or solid-like, but when a tissue is damaged, the cells will actually flow collectively in order to repair this wound. And this is what happens. And it looks very much like a viscous fluid, which is sort of like wetting a substrate.
So Luca, may I ask a question?
Yeah,
in that lovely movie, the cells are dividing.
Yes.
So,
yes,
so in that sense, it's not like water. Water molecules don't divide and reproduce themselves, as far as I know.
Yeah, so these are not so these cells are divided, but are also crawling on the substrate.
Yes.
So, yeah, so both process happens, and well, let's see. So the time scale here, well, is very long, as a matter of fact. So I'm sure that there is some definitely cell divisions in this movie.
And a cell division time would be like an hour, maybe, and for these types of cells.
So these are MDCK cells, and yeah, I believe it's roughly 1 hour. Yeah.
Thank you.
Yeah.
Luca, hi. Sorry, I'm remote. I was going to ask you a question about the value of the stress that's being plotted over here. Is it just the magnitude of the trait? What exactly is being?
So this is just the magnitude. Yeah, it's just the magnitude.
Okay.
Yeah.
Because because in some places likely it's tensile, in some places it's likely compressive, and none of that is being separated out over here.
No. So this is just the max. So they take the square and then the square root of it, and that's what they plot. Yeah.
Okay. Thank you.
Yeah, no problem. So this is another example of flow in cellular systems, which I took from this beautiful paper by Stefan Münster and co-workers. So this is what you see here is the Drosophila embryo. Is relatively early in the stage of development. And what you see is that these cells, there are roughly, a few thousands of these cells, eventually will start to flow collectively and give rise to what it looks like a vortex flow. And at the end of this flow, this flow terminates with the formation of these folds, which eventually will evolve into the features of the fully developed fruit fly. So this is an example. The two of them are two examples of biological processes in which the collective motion of cells is instrumental for life, to maintain life, for instance, in wood dealing, or to generate life, like in the context of morphogenesis.
The time scale here is hours or minutes?
Yes.
Probably hours.
Yes. I don't know why it doesn't say the timestamp, but it's definitely hours. Yeah, absolutely. So these are processes that are important for life, but there are also situations where the same ability of the cells to flow collectively is actually produces threats for life itself. And this is an example here in this beautiful movie. This is really an amazing movie from the lab of Peter Friedel in Nijmegen, with whom I have the privilege of collaborating. And what you see here is a stream of fibrosarcoma cancer cells, which are invading the extracellular matrix of a living mouse. So one of the important concepts in cancer biology that was discovered in the past 10 years is that metastases are seeded mainly and more effectively by clusters of tumor cells, as opposed to individual cells. These clusters are able to undergo what it looks like an odyssey, really. They are able to detach from the primary tumor, invade the extracellular matrix, enter inside the blood vessel, and be transported somewhere else where they see the secondary tumor. And they do it in groups, okay? They do it collectively. What you see here is so the actin is labeled in red, and the nuclei of the cells instead are labeled in green, and what it looks like is what to me seems like a shear flow, okay, inside the channel. So it's important to understand the collective behavior of cellular systems with many possible applications. And to this purpose, to this end, the community has developed a large number of different models, okay? So in these slides, I listed a few cell-resolved models, so models that are discrete, that take into account a single cell, as well as some continuous models. The continuous models are those in blue. The most famous of these models, or if you like, the one that has been most popular in the past few years, is the so-called vertex model, in which the cells are somehow modeled as polygons, which form an irregular tessellation of the plane, and then this tessellation is evolved according to some rules, okay? On the other hand, the continuous model, they all are based on some sort of coarse graining of this vertex model. And this coarse graining attempts to use the same mathematical objects to describe the shape of these cells. There is one thing called the shape tensor, which is essentially like the inertial tensor in mechanics, and try to use these objects in order to describe what happens at the larger scale. Because this vertex model is actually very important also for the story that I'm about to tell, and in fact a variant of this model that is called the Voronoi model, I would like to spend a few words on this and explain what people are doing in the community. So generally speaking, when you have a confluent tissue, confluent means without gaps, without empty spaces, the cells tend to be elongated and have this sort of like polyhedral structure. There is not much deformation that happens in the Z direction of this slide. And so it's possible to somehow think about these systems in terms of the projected area on the plane. Okay, so we can think about cells as they are polygons. In the special case of the Voronoi model, these are Voronoi polygons, so they have special geometrical properties. These Voronoi polygons can be described by two vectorial degrees of freedom. One is the position of the center of mass of this polygon. Let's call this R sub I, and the other one is the direction of motion, so is where the cells are moving. These two variables are evolved according to the simple set of ordinary differential equations. So the first one describes the motion of the displacement of the center of mass. This is the velocity. On the first term of the right-hand side of this equation describes self-proportion that happens with the velocity v naught, with the speed v naught in the direction p, as well as the interaction with the other cells. And the interaction with the other cells is expressed as the gradient of an energy function. So this is something unusual in active matter, but I will explain it in a little bit. On the other hand, the dynamics of this orientation P is essentially a persistent Brampton walk, where eta sub I represents a random number, which is delta correlated, and dr is a rotational diffusion coefficient. Now, the interesting quantity here is this energy E, which is given by this expression that is entirely geometrical, contains exclusively geometrical properties, geometrical quantities of these cells. So here, Ka and Kp are just two constant, two stiffnesses, whereas A sub I is the area of a single polygon, and MP sub I is the perimeter of this polygon. Whereas instead A naught and P naught represents a preferential area and a preferential perimeter. Now, the first time I saw this model, this expression, I was extremely skeptical, I have to say. I said, okay, come on, I mean, this is just too neat to represent something as complex as tissues. But then I realized that this model is actually very complicated, not only because it contains these geometrical quantities such as the area and the perimeter, which are actually rather complicated functions of the coordinates of these vertices, but also because it contains three different processes, okay, of which at least two of them are biological. To explain that is worth to expand this summation and write them.
Sorry, Luca, maybe in the previous slide, I just wanted to ask another question. Have people measured the heights of the actual cells? I would have think that, you know, cells are being extruded or other things are happening, the heights would be inhomogeneous, and that seems like an important variable. So
yeah, so okay, so there are processes that involve indeed the expulsion and the extrusion of cells. For instance, cell apoptosis. When a cell dies, typically is pushed out of the monolayer. If the cell instead, do not die, the fluctuation of the height is actually very mild. I think extrusion is really the only process here that involves like, you know, a dramatic change in the organization of these cells.
I could imagine, you know, epithelial situations where you want to make another layer. You want to squeeze living cells out, for example, and make multi-layers. Does that ever happen in practice?
But you know what? No, it definitely can happen. I mean, there are more than just monolayers of cells. However, one thing to keep in mind is that these epithelia are not vascularized. So they take nutrients only through diffusions. And so the more layers you put, the less effective is this mechanism. So, you know, these epithelial monolayers are actually something real. I mean, maybe they are not necessarily one layer, but certainly not more than a few layers, 2 or 3.
Okay, and then just a quick question about the dynamics of your polarization PI. It's a multiplicative noise, and that just causes it to spin around, or is the length maintained by that equation, for example?
Yeah. So if you write this equation in terms of orientation, in terms of the angle, I mean the angle that this vector makes, say with the x-axis, Then
Yes.
the equation becomes theta prime, let's call it theta, equal to equal to eta. So this is just, yeah.
Okay, so the theta would have additive noise.
Yeah. It's definitely added. No, this is just a way to write it in such a way you see the vector and not the angle, because I haven't defined the angle yet.
All right, thank you.
Yeah, no problem.
Luca, quick sort of question following up on what David just asked, and presumably you will get to that right now. Because if you think of each cell in the epithelium as roughly 3D incompressible, then changing local area would be changing local height.
Precisely.
So in principle, you are allowing for local height variations because you have an AI.
Yeah, exactly. So this is what I was about to say. So these terms can be decomposed in the following way. The first term is actually what I would call a soft constraint on the volume. Okay, so the cells, even the volume is not exactly constrained, but if it was, okay, then we are still looking at the projected area, and the projected area is not conserved, but instead oscillates around, an equilibrium value, which is specified by I naught. So yes, so this is mostly like a constraint on the volume, but it's not an exact constraint. The second term, on the other hand, here, this is proportional to the perimeter squared. Okay, so it's sort of like an elastic force and embodies the contractility of the actin cortex. So this is an energy, so the force resulting from the energy is going to be proportional to the perimeter of the cell. And there is actually evidence, both experimental and numerical, that this is indeed the case. The traction forces exerted by cells scale like the perimeter. The last term, on the other hand, represents the adhesive interaction between cells. Okay, so here Lj represents the length of each junction, so the age which are in common between two cells, and the fact that there is a negative sign here, it means that the system is energetically favored to extend the length of this junction. So this represents precisely the adhesive interaction between the junctions. So there are three different processes, I would say. Well, one is not a process, it's just a constraint in a very simple model. Okay, so this is actually more complicated than it might look like.
And you've
So
dropped an overall constant, I guess, in going from the first line to the second line.
Yes. So there is of course a constant that nevertheless does not contribute to the dynamics. You might ask, where is the activity in this model? Okay, so this is an active system, but where is the activity? Well, it's in three different terms. One is the cell propulsion. So these cells are propelled with some velocity v naught. But then the other activity is in these two terms, okay, namely the contractility of the actin cortex, which is definitely an active process, and the adhesion between the cells. There is also a parameter here, which is a control parameter, which is very important for all the works which are related with this model. And this is the so-called shape index. This parameter, P naught, is the ratio between the preferential perimeter and the square root of the preferential area of the cells. It's called shape index because if you restrict yourself to regular polygons, okay, there is a very precise relation between this index and the number of edges of the polygon, therefore the shapes. And this is the relation. The range of this curve is very small, it's roughly 1, goes roughly from 3.5 to 4.5. And this asymptotic limit, which is around 3.5, corresponds to a circle, so a polygon that has an infinite number of edges, whereas on the other hand, this upper bound here corresponds to a triangle, so only 3 edges. There are two numbers here that are worth remembering, and those are 3.81 and 3.72. 3.72 is the shaping that corresponds to a regular polygon, whereas 3.81 is the shape index that corresponds to a pentagon. So you will see why in the next slide. So one of the important results related with the Voronoi model that was published by Max B in collaboration with Cristina Marchetti and Lisa Manning is the fact that it's possible to see a phase transition between a solid phase where the cells only jiggle around their equilibrium position to a liquid phase, where the cells instead are moving around, are roaming freely throughout the system. And as you can see in these snapshots, okay, so this tessellation, there is an obvious change in the order, okay, in the regularity, I would say, of this tessellation. This transition can be triggered by increasing the shape index P naught or by increasing the velocity V naught. Okay, and the fact that increasing the velocity eventually will make the system fluid is kind of simple to understand. Instead, this is a bit more subtle. I mean, the increase in P naught that will produce such a transition. This transition happens exactly, okay, at zero velocity at the value 3.21 that corresponds to the shape index of a regular pentagon.
So Luca, is this actually a transition, or could it be like a glass transition, something which is gradual? If there were a first order transition in two dimensions, there'd be possibly two-phase coexistence. What is the nature of this thing? I realize you're out of equilibrium, but still, you maybe ask these questions.
You are anticipating my next slide.
I can wait. I can wait.
Yeah. Wait a few seconds, and you will see all about it. Right. Sorry. What I was saying, yes, indeed. So there is this transition, let's call it, and the models somehow that have been, so most of the discrete models somehow are able to capture this transition in one way or another, okay? And these models, these discrete models, are actually also quite successful. For instance, one of the first people to use the Voronoi model or the vertex model in order to explain properties of tissues was Frank Uliger and Reza Farfadir, who use the vertex model in order to say something about the distribution of ages in these irregular tessellations in these tissues. And nowadays, I would say these models are so popular that it's hard to find an experimental paper that does not contain at least a little section where they use these discrete models in order to shed light on the experimental results. Okay. On the other hand, the continuum models are not equally successful, and there are two reasons for that. One of the reasons is that they are newer, okay, and so the community didn't have enough time to understand them fully or to process them, right? But there is also another reason, and the other reason is that hydrodynamics is a theory that revolves around symmetry, and it's unclear what the symmetry of these tissues could be, if any at all. However, these questions, I mean, this puzzle was solved recently, I mean, in 2018 by these two gentlemen, Massimo Picaciamarra and his postdoc Yan-Wei Li, who published this paper on Physical Review of Materials, in which, by doing extremely careful simulations of the vertex model, they demonstrated that the solid phase and the liquid phase are actually separated by an exotic phase. The exotic phase has a very small range, exists in a very small range that goes from 3.81, I'm talking about the shape index, to roughly 3.9. But nevertheless, here is where all the action happens. So it's very important, even though it's very narrow. And furthermore, this exotic phase, by increasing the temperature, and by temperature here, what we mean is the variance of the noise variable in this Langevin equation, so the orientational noise, if you like, in the dynamics, the exotic phase shows coexistence with both the liquid phase and the solid phase. So it's a very complicated phase transition. Here is an example, and of course, I mean, the exotic phase, this is what started here, exactly 43 years ago in 1978, is this intermediate phase that occurs in the melting transition in two dimensions and separates solids from liquid. Okay, and this is the beautiful theory that David and Ben Halperin put together. I just want to make another numerology remark. So this paper was published on the 10th of July, 1978. I was born on the 10th of January of 1978. So when this paper was published, I was exactly 6 months old. 6, like the symmetry of the exotic phase.
Did you have to say that?
Yes. So what is an exotic phase? So as David explained, already a long time ago, when a crystal melts into a liquid in two dimensions, does so in two steps. Okay, first it transitions from a crystalline solid to a liquid crystalline phase that has quasi-long-range orientational order. And then there is a second transition from the exotic liquid crystal to an isotropic liquid. The concept of quasi-long-range orientational order can be defined as follows. So imagine to take a box around your system, around a part of your system, and let's say that this box has a edge length L, okay? Inside this box, it's possible to measure a order parameter that reflects precisely the six-fold symmetry. The order parameter is given by this expression. So this is an ensemble average within the box of the complex function e to the 6i theta. Theta is the direction of either one of these red arrows. So this is an average of a complex number, therefore is a complex number whose magnitude is uppercase psi, and its phase is given by this other theta. Okay, so this represents the average orientation of these arrows. Now, in a normal, long-range ordered system, this quantity would, eventually plateau to a constant value. On the other hand, in quasi-long-range ordered systems, this is a function that scales with the system size L, with the size of the window L, and in particular, it scales algebraically, like in this expression, L to the power minus eta 6 over 2. Okay, eta 6 is a non-universal critical exponent. And therefore, if you look at a very large window, like a window that has, for instance, as large as the system size, so an infinite system, the order parameter goes to 0. So there is no long-range order in traditional sense, okay? But there is something else. This is a beautiful concept in soft matter physics that resonates, okay, with the idea of epithelia transitioning from solid to liquid in two different ways, actually. One way is the soft matter way, okay? I mean, in the end, we are talking about the two-dimensional system. When two-dimensional system melts, they do it through an intermediate exotic phase, so it's not unreasonable to think that they are exotic. But there is also another concept here, which I personally find extremely interesting. Tissues for many years, many decades, have been considered as some sort of two-state systems, okay? A system that contains two states or two phenotypes, if you prefer, called epithelial and mesenchymal. In the epithelial states, the cells are tightly adhering to one another and the system is solid-like. However, in the mesenchymal state, the cells are not as tightly bound, they tend to be elongated and they are able to move, okay? Now, for many years, as I told you, these were the only two states that people knew. And the idea was that possibly cells are able to switch from one phenotype to the other phenotype discontinuously. So this is called the epithelial mesenchymal transition, or the opposite, the mesenchymal epithelial transition. However, recently, and I'm saying very recently, the biologists started to argue that instead that there is no such thing as this discontinuous transition, but there are somehow intermediate phenotypes, or perhaps even a continuum spectrum. In fact, nowadays is not unlikely to hear people talking about the epithelial mesenchymal spectrum, I suppose the epithelial mesenchymal transition. This is something that again resonates with the idea that we have about exotic and about melting in two dimensions. We are in the realm of speculations, okay, but I think it's an interesting concept to speculate about.
So if you could go back 2 slides, I wanted to ask a question, make a comment back further. Yeah, so this interesting phase diagram, I think, has been seen now for Leonard Jones, equilibrium systems, and so forth, with a first order transition from, if I'm reading this right, liquid to hexatic, and then a continuous transition from hexatic to solid. So one of the things that's in that ancient paper when you were 6 months old is that there's a diverging shear viscosity coming from the absence of free dislocations as you go from hexatic to solid. And it looks sort of like a Vogel-Fulcher law, but it's an equilibrium phenomena. It seems to be fairly well founded theoretically. Did this group study the shear viscosity, which is going to infinity in a continuous way, perhaps in this non-equilibrium context, going from the purple phase to the gold phase?
So no, they haven't, but thank you very much for the suggestion, because they haven't, but I will.
Oh, good. Fantastic. That I think could be important biologically, perhaps. to have
Absolutely,
continuously
absolutely.
Variable shear viscosity. Excellent.
Absolutely. Yeah.
Also, Luca, clarification that the
Yeah.
phase diagram, that's an equilibrium simulation of the vertex model.
So this is an integration of the Langevin equations.
But with no self-propulsion.
Without self-propulsion. When there is self-propulsion, then the same phase diagram remains, but then you have another axis which on which you can access the exotic phase. Yeah, but the exotic order is still there.
Okay.
Even with self-propulsion. Yeah. So let me, in fact, talking about that, let me show you how this configuration looks like. So these are 3 simulations that have been done by my great student, Jose Colado. And here you see precisely the 3 phases. And here we have self-propulsion, although it's very little. So this is the solid one on the left, in the center is the exotic phase, and on the right instead is the liquid phase. Okay, and here we are really across this transition, this sort of critical value, which is about 3.81. So once we read this paper, the idea that we had was precisely to try to develop a new theory, a hydrodynamic theory for epithelia that revolves around the hydrodynamics of exotic liquid crystals. Okay, and this is a strategy that has been applied already in nematics, and in nematics it works like a charm. So, you know, the idea was that perhaps here is the secret, here is the key that we need to unlock, okay, the hydrodynamics of epithelia. There is a problem though, and the problem is that there is not much work about the hydrodynamics of exotic liquid crystals, okay, except for a number of pioneering works. One of them, in fact, 2 of them involve the same 2 gentlemen of the previous slide, David Nelson and Ben Halperin, together with another great statistical physicist, this time from Europe, whose name is Annette Zepelius. And I believe she was a postdoc at that time, David. Is that right?
That is correct. And I think she recently won the Max Planck Medal of the German Physical Society.
Then congratulations to Annette. So the equations sorry, the theory of Zepelius, Halperin, and David revolves around these 3 equations. Let me sort of walk you through these equations. So the first 2 equations are very standard, and they represent, so here rho is the density, is mass density, and v is the velocity. And so they represent the standard mass continuity equation and the momentum conservation equation, the Navier-Stokes equation. In the second equation, there is this right-hand side, the left-hand side, sorry, is called the material derivative, is the standard time derivative in a flowing medium. On the right-hand side, on the other hand, we have the divergence of the stress tensor. And the stress tensor here consists of 3 contributions: a pressure, a viscous stress, here eta is the shear viscosity, and u is the so-called strain rate tensor, which is the symmetric part of the velocity gradient. And finally, there is also a stress here, a reactive stress. This is the stress that contains all that embodies all the non-dissipative processes that happens in the exotic phase and that eventually will lead to a flow. Okay, this tensor can be constructed using energy conservation and entropy reproduction consideration, and is given here in this expression. So it's proportional to the derivative, to the derivatives of the angle theta, which represents the average orientation of the exotic director. So in other words, you know, it's possible to deform the liquid crystals in such a way, then the release of this deformation will drive a flow. Okay, this is a standard concept of liquid crystals. The equation for the angle is that, so this again is the average orientation of these exotic arrows. Is very simple. It contains these 4 terms. So the first here is again the material derivative of the theta field. But this is now augmented with another term, omega xy, which is the only non-zero component of the so-called vorticity tensor, which is the anti-symmetric part of the velocity gradient. And this construction, that together is called co-rotational derivatives, guarantees that the angle theta behaves as it should with respect to rigid body rotations. On the other hand, this term on the right-hand side represents the relaxational dynamics of this phase. So, you know, the dynamics that eventually will lead to a minimum of the free energy. Okay, it's the classic diffusive dynamic. K here, which is the same constant here, is the orientational stiffness of the exotic phase, whereas gamma, on the other hand, is the orientational viscosity. Now, here is peculiarity. These equations, what is the symmetry of these equations? Okay, the symmetry of this equation is O2, namely that you can take the phase theta and rotate it by an arbitrary angle, which is uniform throughout the system. Okay, and this symmetry is actually a bit too much, a bit more than what you need in order to describe the exotic phase. Or if you prefer, there is no term in this equation which is specific of the sixfold symmetry of exotics. Now, there is a reason for that. Of course, I mean, these three people do not make mistakes. And the reason is that the focus of these papers was the hydrodynamics of the melting transitions. So there is a critical point. And as we learned somehow 9 years before this paper was published, if you are close to a critical point, there are only a handful of relevant terms and many, possibly infinite, irrelevant terms. Okay, namely terms in the equation that do not produce any effect on the macroscopic scale.
Just a small comment, Luca, the sixfold symmetry is sort of comes in a mild way in the one Frank constant approximation is exact, is something with sixfold symmetry, unlike an atomic.
Yes, thank you for this clarification. Yes, indeed. Unlike pneumatics, I mean, this type of liquid crystal, there is no difference between bending and splay, for instance, and therefore there is a single elastic constant. Yeah, absolutely. Nevertheless, somehow we were not sure that the same assumptions that led to this equation are also the same that happens in epithelia. Okay, and so if nothing else for curiosity, we wanted to see what else could be there. And so in doing so, we developed a generic hydrodynamic theory, not just for exotic, but once you do it for 6, then you better do it for everything, right? And so for p-adic liquid crystals, which are two-dimensional liquid crystals with p-fold rotational symmetry. Now, this seems like a bit of an academic problem, but as a matter of fact, all these liquid crystals have been actually synthesized in the lab, and the soft matter people have really done an incredible job. My favorite one is this pentatic liquid crystal that was done at the lab of Thomas Mason at UCLA by using lithographic techniques. They first somehow printed a pentatic quasi-crystal using the dye kite and darts Perrot's tessellation, and then they let the system undergo Brownian motion, so the pentatic quasi-crystal melts into a pentatic liquid crystal. Instead, this also is an amazing piece of work by the lab of Roel Doelens at Oxford, in which they really, push the boundary of understanding the melting transition at the experimental level. Here, what you can see is a coexistence. So these are colloidal spheres, okay, and this is what is showing is a coexistence between exotic phase and the liquid phase. Now, how did we do that? So how did we go beyond this theory? Well, we simply did what people typically do in nematic liquid crystals. So, okay, so nematic liquid crystals are p-adic liquid crystals when p is equal to 2. So imagine to have a nematic liquid crystal and to zoom on a little piece of it. What you will see is a bunch of molecules which are elongated and they are roughly aligned along the same direction. So we can think about them as rods, and we can call nu. Okay, we can indicate with letter nu a unit vector that indicates the average orientation of these rods. Nevertheless, all the physical properties of this phase are insensitive to the direction of this vector, but depend only on the orientation. So in order to encode that into a hydrodynamic variable, what we can do is to construct the so-called nematic tensor order parameter. The nematic tensor order parameter can be constructed in this way. We can take nu, multiply tensorially by itself, and take the ensemble average again at the microscopic scale within a single volume element, and then make this tensor traceless. Okay, so this double bracket that I wrote on these slides is an operator that makes whatever is inside it symmetric and traceless. So in this case, the tensor is already symmetric, but nevertheless, we'll make it traceless. So if we transform nu into minus nu, okay, the sign cancels and the variable does respect the twofold symmetry of the nematic phase. This quantity can be, we can compute the ensemble average. If we do that, this will produce an order parameter. Okay, this order parameter is exactly the same order parameter you would get by taking the average of this exponential function e to the I2 theta times another traceless and symmetric tensor, which I indicated in this way, where n is the so-called nematic director, which represents the average orientation of these rod-like molecules. Okay. Now, this construction, which is indeed very well known and very successful, however, is not unique of nematics, but can be extended to any p-adic liquid crystal. You just have to take this tensor product not twice, but p times. Okay, so let me indicate this operation with this different type of notation, nu to the tensorial power p, then we can take the average, and then we can take the trace. Okay. And then we can make these traceless. And eventually this will give something very similar. So an scalar order parameter, which is exactly the same one that you would compute starting from other consideration, times this traceless and symmetric tensor that embodies the average orientation of the p-adic director. Now, you might think now that working with high rank tensors is actually fishing for troubles, okay? Because in 2 dimensions, even if the tensor is symmetric and has rank p, this tensor has 2 to the p minus 1 components, okay? Different entries that for the case of hexadics, for instance, gives 32 different hydrodynamic variables. It's a bit too much for a human, that maybe for a machine is not. This is not true actually, because the traceless condition, okay, reduces the number of these variables to 2. So there are only 2 linearly independent components in this tensor, which happens to be exactly the real and the imaginary part of the complex order parameter, namely the ensemble average of this function here. Okay. So you may think, okay, great, but then, I mean, if you can get the same information from a complex number, why do you need the rank 6 tensor? The reason is that this tensor has a lot of structure. Okay, and this structure is extremely helpful to construct the hydrodynamic equations, because on the left-hand side, you have a time derivative of the tensor. On the right-hand side, you have all the possible combination of this tensor and the tensors that represents the flow field. And because there are not many of this combination that satisfies this algebraic properly, the equations almost write themselves down. Okay. So here is the equation that we managed to write down using these different approaches, alternative approach. The first 2 equations are the same as in David's paper, so I will not even explain them. I would like to focus instead on this last equation, which looks very ugly, but this is also because this is only because we wanted to be generic and to do this for any p-value, and so we had to use operators like this one. So this is a floor function, returns the integer part of p over 2. This is a mode function instead, and is equal to 0 if p is even, and to 1 if p is odd. Okay. This equation.
Sorry, Luca, can you remind me what the variable u is? V is an advecting velocity for this tensor, but what is u?
U is the strain rate tensor.
Strain rate.
Strain rate, exactly.
And it's symmetric. It's a symmetric tensor then.
It is a symmetric tensor and is indeed the symmetric part of the velocity gradient. So yeah, so partial I Vj plus partial J Vi.
And if it's and is it legit? I mean, coming back to the earlier question, the trace of u is the divergence of a velocity field. Yes.
Absolutely.
But that's not the same as the velocity field v, or the same v comes in.
It is
derivatives to u.
It is the same v. It is the same.
Thank you very much. All right.
Yeah, it is the same v. So let me explain a little bit this ugly equation. On the left-hand side, what we have is exactly the same quotational derivatives that David wrote, but just expressed in terms of this tensor. Okay, but nothing more than that. On the right-hand side, the first term is also nothing more than what David has done. It's the derivative, is the functional derivative of free energy, and represents the relaxational dynamics of this p-adic phase, okay? And the free energy here can be written, for instance, in this Landau-Degent form. So the real novelty in this expression are the last three terms on the right-hand side, which represents different ways in which the p-adic order couples to a flow. The first one is a coupling between the order parameter, okay, the scalar order parameter, and the flow field is 0 in the case of incompressible flow. This does not affect the orientation, okay? On the other hand, the last two terms affect both the order parameter and the orientation and are what I would call flow alignment terms. Now, these flow alignment terms are strange, okay? At least one of them is very strange. And I don't even fully understand them. And namely, okay, my understanding of these terms still has to be completed. But nevertheless, I would like to flash a few properties of this term. So the first one is linear and scales like a length to the power 1 minus p. So when p is equal to 4, as a matter of fact, or larger, this term, okay, scales to 0, decays to 0 more quickly than any other term here in these equations. That's for this reason is irrelevant in the RG sense. Furthermore, this term is always reactive, so does not lead to any entropy production. The second term instead is nonlinear. It's a nonlinear function of u, okay, and except in the case p equal 3, it scales like a slightly smaller power. So this is hard to decipher, but this number is 2 for p equal 3 and p equal 4, and 3 for p equal 5 and p equal 6. And
sorry, the brackets mean the greatest integer you can get from p over 2? Is that what the brackets?
Sorry, David, say again.
So the brackets in the second gold equation on the right-hand side, that means the greatest integer that you can get from p over 2?
Yes, exactly. The smallest integer. Yeah, the smallest integer.
Like round down.
So so this term scales, goes to 0 more quickly than any other term in these equations. And what I find the most controversial peculiarity is that it can be either reactive or dissipative depending on the p-value. Okay. So for instance, for triadics, so p equal 3, these two terms are the same. For tetradics, this is going to be just u to the tensorial power 2. And so this means that the term will be dissipative, so will be for p equal 5, and will be reactive again for p equal 6. I frankly don't understand that, okay? But, you know, there is something that you know, we'll have on our agenda. Now, before going back to epithelia, I would like to show you, time has run, unfortunately, a couple of results. Okay.
But I think you started 15 minutes late, so so you have more time than you might think.
Luca, can I ask you to go back to the previous slide? You didn't tell us about how sigma r looks like in this general situation.
I know. I didn't tell you because it's like a headache.
Yeah, because unlike in the previous, in the hexatic case where you just have one contribution, which is a Laplacian of the angle, and another one, which is the grad cross tensor, here you'll probably get this huge mess.
So this sigma r can be calculated using exactly the same principles. It's just, you know, an ugly expression, which.
But you have a lot of constants which are uncontrolled, or not.
We have, yes, absolutely. We have constants whose values is unknown. Yeah, precisely. Yeah.
But Luca, sigma r, if you derive it from the free energy, and you write it in terms of the angle, so take QP, make it in terms of the angle and the order parameter, and if you forget the amplitude and just keep the angle, then it should reduce to what you wrote previously, right?
If you neglect this term and this term, yes.
No, sigma r alone. Sigma r doesn't have anything that has the strain rate tensor sitting in it, right? Sigma r is just the elastic stress from the free energy.
That's true, but it does contain terms which are proportional to this, not to you.
Okay. Simply by virtue of the reactive components that will match. Okay, fine. Thank you.
Here we go. Yeah, absolutely. So I want to flash a few results about passive p-adics, okay, before we move to epithelia. One result which I think is interesting, although not completely unexpected, is the following. I told you that at equilibrium, p-adics are in general a quasi-long-range order. So this means that the scalar order parameter decays with the length scale at which is probed through this power law. Okay. Now, imagine to have now a shear flow, a simple shear flow with a constant shear rate. Let me call it epsilon dot. The effect of this shear flow is actually to introduce another length scale, a length scale which is proportional to the square root of the rotational diffusion coefficient of the p-adic phase. So the combination of these two constants is a rotational diffusion coefficient divided by the shear rate. And as a matter of fact, this constant, this new length scale replaces this length scale in the expression of the scalar order parameter in such a way. Now the order parameter does no longer decays with the system size, but remains constant. And it scales like the shear rate to the power eta p divided by 4. Okay.
Sorry, what is big L?
So a big L is the orientational stiffness. So it is the coefficient in front of the gradient squared of the.
Thank you.
Yeah. I'm using here some notation that is used in the Barry's-Edward theory of pneumatics. They call it L for some reason and not K. Yeah.
Okay.
So is it fair to say that because you have a shear, you have shear axes when you take the shear tensor and diagonalize it, and those couple to the order parameter, the p-adic order parameter, and thus endow it with long-range order that it inherits from those shear preferred directions.
That's absolutely right. That's precisely right. Yeah. Yeah.
And how many of the new transport coefficients play a role over here, or is this just from the vector?
So good question. So let me show you this plot first. So these results, which I just hinted so far, can actually be demonstrated by analytically computing the correlation function. Okay, the correlation function and the order parameter in the presence of shear. This is a calculation that can be done exactly if the equations are linearized. So the linear theory can be solved fully. And instead, it's possible to use RG in order to demonstrate that nonlinear terms that we neglected are actually irrelevant in the RG sense, provided the shear rate is sufficiently low compared to the typical relaxational time at the cutoff length scale. Okay, so to answer your question, there are no renormalized transport coefficients that play a big role here. The correlation function. So here I've been plotting the correlation function for different values of A over LS. So A here is the cutoff length scale, so the length scale at which the hydrodynamic theory breaks down. LS is the shear length scale, so it's this additional length scale. This curve here corresponds to the case in which there is no shear, and so the correlation function decays algebraically. So this is a log-log plot, just like in equilibrium systems. But as you can see, as soon as you add shear, and even like an infinitesimal shear rate, will eventually lead this curve to plateau, okay, to a constant value. And as you can see, these curves are actually overlapping all the way to a specific length scale, which happens to be precisely LS. So fluctuations are suppressed by shear above this shear length scale. The order parameter just satisfies the property that you would expect from the previous consideration. So this is one result about passive p-adics. Let me show you another result very quickly. So imagine to have a channel now and to put like p-adics inside the channel. Using the typical approximation of channel flow, it's possible to reduce those complicated equations to this equation. And these equations have also some, constant bulk solutions, which are obtained by setting this term, you see this parenthesis here, equal to 0. Here, EC is a constant with dimension of shear rate, which combines various constants from the previous equation, especially the coefficient of this nonlinear flow alignment term. Okay, now this is a phenomenon that already exists in pneumatics. It was already known in pneumatics, but actually it seems to us that it exists also for all p-adics. The angle at which the flow aligns is not universal, but nevertheless, if you really crank up the shear rate by increasing this number a lot, eventually the solution of this equation is the zero of this sinusoidal function, which, for instance, in the case of exotics, happens to be plus or minus pi over 12, plus or minus, depending on how the shear flow, whether it's increasing with y or decreasing. Okay, and those are somehow predictions that could be tested. Now let's go back to epithelia. Okay, so now that we have such a construction, we want to sort of adapt it to describe the hydrodynamic. Yes.
Luca, sorry, 1 second. I have a question before you go to the active case.
Please.
Just like in the nematics, can you have, so presumably your lambda p and nu p can be of either sign? And do you have, is there an analog of flow aligning versus flow tumbling? Depending on.
So yes, I mean, there are many analogs of that. It depends, however, on many things. Okay, so for this channel flow, okay, which is actually very simple flow in which the shear rate is constant, okay, is uniform throughout the system, then no, I mean, there is no such a difference. But as you can see from these equations, the system is actually is both flow aligning and flow tumbling, depending on the shear rate. Okay, in this case, the behavior also depends on the specific p-values. So for certain p-values, you can see the typical tumbling. In this paper that I have listed on the previous slides, we also have done like a stability calculation to compute the shear rate at which the system starts to tumble. We also have worked out the case of a Taylor-Couette flow. So in this case, it's different. To me, is more interesting because of the circular geometry of the Taylor-Couette cells. Then the shear rate is actually always is never uniform. Okay, and this produces flow alignment on all p values. Okay, and in particular, there is a prediction for p equal 3, which I think it should be looked with some attention, because that would be a way precisely to measure these unknown and mysterious nu-p coefficient parameter.
And even for nematics, although we typically never write it, because you also have a density equation, you had a continuity equation for the density. Mm-hmm. So we can couple, even in the free energy, you can have a QP times gradients of densities times power to P, right? And then there could be flow alignment or alignment to density gradients potentially.
Yes, well, that is possible. I mean, we try to keep the thing as simple as possible because they're already very complicated.
Yeah, okay.
Okay, so let me move to epithelia. Okay, so now that we have this framework, we want to use this framework in order to account for activity. Okay, and again, following the same philosophy of active nematics, this can be done very easily. Okay, you just have to forget about the other two equations and enter, augment the momentum conservation equation with a single quantity, which represents the so-called active stress. So this is the contribution to the stress tensor due to the fact that particles, so in this case cells, are able to exert a contractile or an extensile stress. Okay.
And then so there's a friction term at the end, which you're talking about. Tell us about. What about anything? How hard would it be to incorporate cell divisions? You'd have source terms in the density or something?
Exactly. Yeah. I mean, both cell division and apoptosis can be included in this model by adding like a linear term, Ka times rho here in this equation. Yeah.
It'd be interesting just to see what happens. I mean, in a sense, those cell divisions are a way of giving enhanced mobility to dislocation climb, because if you're adding cells, then you let the dislocation dynamics proceed more quickly under cell division. I can imagine there could be interesting effects there.
To the dislocation glide, yes. Sorry, I'm writing things down, David, because those are all absolutely wonderful suggestions. I mean, our achievement so far is mostly to write down the equations, but there is everything to be discovered here. So
very interesting.
I will definitely add this. So this is the active stress instead. And the active stress here can be again computed phenomenologically. And this is another reason to have this funny, p-fold tensor, okay? Because now with this tensor, we can actually compute, we can model the stress by just constructing the simplest combination which have the right symmetry. And there are two of them. One involves only the order parameter. So the square of, with this symbol here, I mean like, the contraction of QP with itself, which gives the square of the order parameter. So this is a contribution to the stress, which is due to the local variation of the order parameter in the system. Because the order parameter is typically uniform, okay, at least in the Landau, the Gen, hydrodynamics, we expect this term to play a little role, except in the presence of defects. Okay, and so this is something that I would like to explore in the future, perhaps just with maybe in combination with what you said, David, about cell division and dislocation glide. The second term, on the other hand, so excuse me for using this unconventional notation, but I guarantee that it's better that if you write that with indices. So this dot here corresponds to the contraction of all the indices of this tensor with all the indices of this tensor. And if these two tensors have different rank, this will be a tensor itself whose rank is the difference between the ranks of these two tensors. So in this case, it's P minus 2 equal 2. Okay, so like the rank of the stress tensor. This second tensor, which as you can see involves high derivatives of the order parameter tensor, can be also computed out of a microscopic consideration. So if you imagine to have an hexagon, okay, an hexagonal cell, which is sort of like exerting forces in these 6, equivalent directions, then upon coarse graining this force, you will get exactly this term, okay? Now, let me, so these are the questions that somehow governs the dynamics of these systems. But there is something else to be added here, okay? Namely, what is the p-value that we have to include? Okay, so these are the questions for generic active p-adics. But when we talk about epithelia, what is the p-value that we have to include? Okay, so Lee and Pika Chamarra told us that by doing these beautiful simulations that there is an exotic phase. So when the tissue is solid, okay, it is essentially a six-fold symmetric crystal, okay? On the other hand, in this intermediate phase, it could be an exotic phase, but then when you are far away, I mean, toward the end of the epithelial mesenchymal spectrum, then the cells tend to be elongated, tend to move in a specific direction. So it's possible that indeed the system is also nematic. Okay, so in order to capture this concept, we try to combine essentially these two different types of liquid crystalline order, exotic and nematic, into a single phase that we like to call hexanematics. Okay, it's not an official terminology, but feel free to disseminate it. So these are our hydrodynamic variable, the density, the momentum density, the nematic tensor, and the exotic tensor. Okay. Because we are...
So look, just returning to the biological motivation, when things are fluid, whether they be hexanematics or whatever, that presumably is relevant for cancer, for example. If you fluidize a growing mass of cancer cells, they can then migrate to other parts of the skin or whatever.
Absolutely.
Okay.
Absolutely. And I'll tell you more, David, there are a lot of works in the literature that have tried to look to understand the dynamics of mesenchymal cell layers treating them as active nematics. Okay. And, people have tried also to compute, to locate the defects and to convince themselves that indeed you have this +1 up and -1 up defect and so on. But this is not the full story. Okay. This is not the full story. Once we include two different types of liquid crystalline order, we have to account for the possible coupling between them. So one way to couple them is through the flow, but then there is another coupling that you can include directly in the free energy. So this is this third. So this is a Q6, and this is the nematic tensor to the tensorial power 3. So contracted with one another, they have this. This is a scalar, and this scalar is conveying some sort of like alignment, a mutual alignment between the director, the nematic director, and the exotic director. And
Luca,
finally,
question about the interpretation of the Q2. Are you thinking of, or should one think, or should I think of the Q2 as you mentioned earlier, as alignment between elongated cells, or are you thinking along lines of what people have done in these coarse-grained models, the vertex models, where there's a shape tensor, which if you make a traceless also behaves like Q2, but then it doesn't describe alignment, it describes anisotropy of skeletal cells. Which, or both, or what's the interpretation that you're thinking of in this formulation?
So the interpretation that I'm thinking of in this formulation is that there is an intermediate configuration, which is somehow more or less here, in which the cells are elongated hexagons. Okay. These elongated hexagons tend to align with one another, thereby forming something that at least is close to a nematic phase. And this also affects the way they move. Okay, because this is something I didn't explain in the interest of time, but the way cell moves is in confluent systems is by intercalation, so by exchanging position. So there are topological changes in this network as the system flows, and these topological changes are affected by the shape of the cells. So to me, the two concepts are not entirely separated, but the way I think of them is mostly because of the shape. Yeah.
Okay.
So we slowed you down a lot with questions, but probably should be wrapping up soon.
I will. So okay. So let me give you. So what we have derived the equation. Then what we have done with them? We have tried to validate them. Okay, and to validate them, we used the structure factor, which is the most old-fashioned thing that you can do now. People do machine learning nowadays. Instead, we do the structure factor, and by the structure factor, what we found, okay, is that there are signatures of liquid crystalline order at different length scales. And in particular, let me somehow, move away these terms. It's possible to see that at the small length scales, there is this Q to the 6th term, which convey the hexagonal structure of the cells. Whereas on the other hand, at the large scale, okay, the structure is dominated precisely by this nematic order. And this term with this 1/Q² dependence is representing what in active matter physics is called giant density fluctuation. It's called giant density fluctuation because for a uniform system, at a large length scale, the structure factor should go to a constant, indicating that the system is uniform. Instead, here, the structure factor diverges. Is it possible to compare that with the discrete simulation? Yes, we have done it. So what you see here is the same structure factor computed using the vortex model. Small scales are very well fitted by this Q to the 6th power law. On the other hand, the large scales are fitted by an inverse power. Here you don't have to, so this is roughly -1, and don't have to think about this value of this number too much, but focus on the fact that this is nowhere close to -2, which was our theoretical prediction. But nevertheless, this is a known issue in active matter physics. And in fact, even if you look at the nematic version of the Vic-Check model, this linear theory predicts Q to the power -2, whereas instead numerical simulation gives Q to the power -1.2. And why is that is not fully understood. So this is one of the preliminary results, but of course, the best results are those that come from experiments. So I have the privilege of having in my group an experimental student, Julia Eckert, and Julia has been doing experiments with MDCK, sorry, here I misspelled it, cells, and by computing precisely the nematic and exotic order parameter at different length scales. And by the way, this can be done with the shape tensor. To do this, on the other hand, we had to generalize the shape tensor to generic symmetries. And that was non-trivial because, concepts such as eigenvalues, eigenvector, the spectral theorem, that are all useful to draw these rods do not exist for tensor whose rank is larger than 2. Here is another comparison. So this is the probability distribution of the order parameter at the scale of the cutoff, at the smallest scale. This is experiment, this is simulation, and these two probability distribution, at the very least, they look alike. Okay. And here is another beautiful data set. This is again the order parameter, but this time versus an increasingly large length scale. So the blue dots here correspond to an hematic phase. The red dots correspond to an exotic phase. Okay, so these are experimental data. And as you can see, there is a crossing, which is around 30 to 40 microns. Okay, which precisely correspond to the fact that the length scale, the short length scale physics is dominated by this exotic order, whereas the large length scale physics is dominated by nematic order. Okay, so this is our understanding of this phenomenon, but it's still a work in progress. So let me wrap up. So hydrodynamics is a very powerful and predictive theory. Okay, and the first time I went to a talk about it was a guy from Kodak, actually, the film manufacturer, who explained how to use hydrodynamics to do inkjet printing, and I was literally amazed by how predictive and precise can be hydrodynamics. Where are these going to lead us in our understanding of tissues? Okay, so confluent epithelial layers can be thought, as far as we understand, as active exanematics, namely, active liquid crystal that nevertheless occur at different scales. Okay, and finally, multiscaling is a very fascinating topic and very fascinating concept in physics, and it's not unique to tissues. I mean, for instance, think about intermittency in turbulence. There are so many open questions about this. Okay, for instance, how you connect these different scales. For instance, are these scales somehow related with this epithelial mesenchymal spectrum? So far, we have no answer to any of these questions, but you can bet your house that we will work very hard in the future to get these answers. And by that, I would like to thank you. I mean, the funding agencies. I mean, so this work has costed a lot of money to the taxpayers, both in the Netherlands and in Europe. But nevertheless, it was a great investment because it was an investment in the development of these very bright young researchers in my group, and also, to some old collaborators. And thank you for your attention.
Thank you for the wonderful talk. I know we've asked like a lot of questions, but is there any final questions from either physical or Zoom?
I want to ask about the vertex model. Why does the model you started with, why does P naught and A naught not change when water flows in or out of the cell?
So you asked me about the original, so the Voronoi model, and so this thing here. I didn't get the answer. The question is this what?
Yeah, about that. What the next slide? Wait a minute. Yeah, why is A naught and P naught not changing time?
Well, I mean, it makes more sense if you write it like this, actually. Okay, so here the true variable, the things that are changing are the perimeter, okay, and the length of the junction. P naught, this preferential perimeter is you can think of it mostly as a sort of stiffness, okay, as a constant that tells, how, for instance, how strong, okay, are the adhesions between different cells. Okay, so in this respect, it is not, particularly surprising or insightful. A naught, why A naught doesn't change? Well, this is actually a good question. I mean, because it is true that somehow the shape of the cells, once they are packed in this very tight layer, does not change. So remember that this is sort of like a way to implement a constraint on the volume by working with the area of the cells rather than the volume. But I imagine that the volume of the cell or the area or the A naught also depends on how tight they are, okay, and how compressed they are, and so on. So I'm not sure how good is this approximation, but it's a standard approximation of this model.
I mean, just to follow up on that question, I guess if you have added salt of some kind, and there could be biologically relevant reasons for adding salt, the cells might want to swell as a result of that, and then you could imagine the dynamics of you couple to a concentration of some salt, and then A naught depends on the salt concentration.
Yeah, absolutely. There are also beautiful experiments in which people have actually taken like this monolayer and then they compressed it from top.
Yes.
So the cell extends laterally, and this sort of this forcing has been shown to actually drive a transition from solid to liquid, but it's a different one. So they call this the unjamming transition. by pressure, which is a bit different from this transition driven by this parameter P naught. Yeah.
Luca, can I ask one last question now that this slide is over here?
Absolutely, Mohan.
Very, very nice talk. This idea seems to have connections to some ideas of using area and perimeter to sort of characterize what's going on. Has a connection to integral geometry, and in particular this result of Hadwiger, perhaps you're aware of, which says that in 2 dimensions, in fact in n dimensions, you need n+1 functions to essentially completely characterize patterns. And so in this case, in 2 dimensions, the area, the perimeter, and the Euler characteristic, if I'm not thinking about the interior, is sufficient. And so a question that this raises immediately is whether or not anybody has thought about the third part, the Euler characteristic, and therefore the topology of the pattern. If I'm thinking about emulsions, so if I have cells and extracellular matrix, then how much of it is cells and how much of it is extracellular matrix? Because the assumption that you made over here was all confluent epithelial cells, which are one kind of tissue, but not the only kind of tissue.
Absolutely, absolutely. Not that I'm aware. So this is a very, very, very interesting concept. And as far as I'm aware, I haven't seen anybody mentioning the Euler characteristic. And it is true. I mean, I would tend to think that most of the cells have this sort of like spherical topology, although they don't look like spheres. But I'm sure that there can be also variance here. And if nothing else, I mean, cells have ports and so on, so they actually are able to open up or close, in order to, for instance, let fluid pass. So I don't know, but I think this is very interesting. And furthermore, here we are still in the framework of eukaryotic cells. But I bet that if you also take a look to the prokaryotic kingdom, then you'll see a lot, because I mean, people have genetically modified all kinds of bacteria, for instance. So I would not be surprised if there was like a bacteria shaped, for instance, like a cylinder or something like that. So I don't think anybody have done it, but it's certainly something that is interesting to look at it.
Thank you.
Yep.
Great. Any final questions? Okay, I guess so. Let's thank Luca once again.
Yeah, thank you very much. And well, so thank you for inviting me, and have a good rest of the day. I'll go to have dinner instead.
Right, yeah, and then.
Right. Thanks a lot.
Bye.
Bye-bye.
Thank you so much, Luca.
Bye, everybody.